So thermochemistry, the topic of this chapter, is the study of the relationships between chemistry and energy. So thermo, like heat is a form of energy. So let's review. We've talked about energy and work before, I believe. Energy is the capacity to do work. Work is a force acting over a distance. And heat is the flow of energy caused by a difference in temperature. So energy can be exchanged between objects through contact. So you hold a cup of hot coffee in your hand. The coffee is hot, it transfers energy to the cup transfers the energy to your hand. You feel the warmth coming out of that, right? If you roll two billiard balls together and they run into each other, they both have kinetic energy, and depending on how they hit, the energy can be transferred from one to the other, or they may both just bounce off and keep their own kinetic energy. So we can think of energy, because this is confusing. There's heat and work and energy, and they're all kind of squirrely to define, right? So let's think of energy as something that an object can possess, something an object can have. I think of energy as being a lot like money, right? You can have money, you can transfer money to another person. So a billiard ball rolling across a table has energy due to its motion. It has kinetic energy. Heat and work are the ways that an object... Yeah. The train. So heat and work are ways that an object can exchange energy with other objects. So in terms of money, you could think of, well, like Venmo is a way you can exchange money, but you could also exchange money by giving someone dollar bills, right? There's different ways to exchange money. Heat and work are ways to exchange heat. Sorry. Yeah, that's helpful. Heat and energy are ways to exchange energy. I screwed that up again, didn't I? I'm going to try reading it. Think of heat and work as ways that an object can exchange energy with other objects. Oh my goodness. So the first ball collides with the second ball. It transfers energy to the second ball, and the second ball rolls away. So energy can move into an object or out of it. Money can move into your wallet or out of it, right? So kinetic energy is energy of motion. Thermal energy is energy associated with temperature. And temperature is a form of kinetic energy because all the particles in a solid, a liquid, or a gas are moving. And if we increase the temperature, we increase how much movement there is. In a gas, then they're moving faster through space. In a solid, they're going to be vibrating more. And so they have higher kinetic energy. And that is, we detect higher kinetic energy in a substance as it being warmer. Yes?
I had a question. When something is moving fast and it like pushes other things out of the way, is that it transferring energy as well?
It would be, yes. Yeah, so like if I push this stool out of the way, I actually did work on the stool. I pushed it through a distance. The billiard ball, where it just hits another ball, is just transferring the energy, but that's also kind of a form of work. Yeah. So there's thermal energy, and potential energy is energy that's stored, often due, we think of it as being due to position. There's something I can draw. So this eraser, right? You hold the eraser out, and what's going to happen if I let go? It's going to fall. Does it? Yeah. So it has potential energy when I'm holding it out, And when I let go, its potential energy gets smaller and smaller as it goes to the floor, but its speed becomes greater and greater. Its kinetic energy is increasing. So you just witnessed potential energy being transformed into kinetic energy. It was so exciting, wasn't it?
They're inversely proportional?
Well, it's not that they're really proportional, but there's a fixed amount of energy. So it could be all potential energy or all kinetic energy, or we could be in the process of moving from one to the other. So that's potential energy. Chemical energy is another form of potential energy, but now it's not because something is raised above the surface of the Earth. It has to do with the positions of the electrons and the nuclei in the atoms and molecules. So we could think of some compounds as being like compressed springs. You know, imagine a big spring and you've pushed it down and it's just like literally coiled and ready to spring up, right? And if you release it, it's going to go boing, right? Some molecules are like that. They have a lot of stored energy, like gasoline, and you light a match and it suddenly is going to release that energy. So the chemical energy is also a kind of potential energy. So this is a summary of energy, the capacity to do work. There's kinetic energy due to motion. Thermal energy is a subtype of kinetic energy. Potential energy due to position or composition. Chemical energy is a form of potential energy. And here we're looking at the positions of electrons and nuclei. Yes?
Is potential energy only for objects, not people?
Well, people are objects. That's a controversial statement. You can think of a person as an object, but we can have potential energy too. Like, you know, if you're standing on top of the building, you have potential energy. And if you lose your balance, all the analogies don't work very well. Like people running into each other, it's just not. Yeah, maybe football players, right? Yeah. So, we've talked about the law of conservation of matter. There's also a law of conservation of energy. So, energy cannot be created or destroyed. It can be transferred from one object to another, and it can be transformed from one form of energy to another form. So here they're sticking with the billiard balls, gravitational potential energy. As this falls to the table, its potential energy is turning into kinetic energy. Here's the spring. You compress the spring, now you've got mechanical potential energy pushing that down. When the spring is released, it's going to spring up and move that ball that's sitting on top of it, and now there's kinetic energy because the ball got pushed into the air. So we talk about these because these, examples, because those are things we can imagine. You can picture those in your mind. Picturing the electrons and the protons doesn't help so much. So when we're looking at energy, we're looking at the exchange of energy between different things. And so we have to define what are the things we're looking at. So we typically talk about the system and the surroundings. So the system is whatever that piece of the universe is that we're interested in looking at. And we can define that any way we want. So you could define the system as your hand. Oh, I'm sorry, I'm jumping ahead. We could define the system as the iron in that hand warmer, right? Then the surroundings are everything around it that it can exchange energy with. So it can exchange energy with your hand, your glove, the air in the glove, the air outside of the glove. And technically the surroundings would be the entire universe, right? But the exchange past, a foot or two is so small that we can ignore that. So we identify the system, and the things around it are the surroundings. So conservation of energy means that however much energy is gained or lost by the system has to be lost or gained by the surroundings. Just like with money, right? I can give you a $10 bill and you can take it. You've gained a $10 bill and I've lost a $10 bill. But we can't just suddenly both get $10 bills. And thankfully also we can't just both have $10 bills vanish into thin air. You know, sometimes it seems like money just goes away, but it doesn't really. So the total amount of energy is constant. So if we imagine an energy gauge, kind of like your gas gauge, for the system and the surroundings. Here, starting out, we've got the system at half full and the surroundings at 1/4 full, and they exchange some energy. Now the system is at 1/4 and the surroundings are at 1/2. But the total amount of energy is the same. Do you see that? So the total amount of energy here was 3/4 of whatever that whatever this amount is. And down here we still have 3/4. It's just that we've moved it from one place to another. So energy is something that can be quantified, and so of course we have to have units for it. An object moving at a speed will have a kinetic energy. So m is the mass of the object and v is the velocity of the object. The kinetic energy is equal to 1/2 mass times volume squared. So if we use the base units of the SI system, mass is measured in kilograms and velocity, distance and time are measured in meters and second. Then we get 1 kilogram meter squared per second squared, because that would be the velocity in meters per second squared times the mass in kilograms. And, to avoid just writing kilograms meters squared per second squared all over the place, they gave it a name, and it's called the joule. Joule, and the symbol is capital J. So 1 joule is a kilogram meter squared per second squared. You do not need to remember that. It's actually a relatively small unit. If we think about a 10-watt light bulb, which is not a very bright light bulb, that's going to use 36,000 joules of energy in 1 hour. So it's a small unit. And of course, we can use metric prefixes with it. So we can talk about a kilojoule. Kilo stands for 10 to the 3, or 1,000. A kilojoule is 1,000 joules. Another unit of energy that you might be more familiar with is a calorie, right? There's actually 2 kinds of calories. There's a calorie with a lowercase c, and there's a calorie with an uppercase or capital C. So these are the calories we use in science. That was originally defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. 1 calorie is exactly equal to 4.184 joules, and that's abbreviated CAL. The nutritional calorie, which is what it says on your bag of peanut M&Ms about how many calories per serving, has a capital C, and the abbreviation is capital CAL. So on an exam, capital C and lowercase c are different, and if it looks funky because why is there a capital C there? It's not a typo. It's the other unit, okay? So we refer to those as nutritional calories, and those equal 1,000 regular calories. So a nutritional calorie is really a kilocalorie. We're not going to do much with nutritional calories, but they show up in some worksheet and homework problems. There's a larger unit called a kilowatt hour, kWh, and that's what PG&E uses to measure the electricity that you're using on your electric bill. So this just kind of gives you some relationships between calories and joules, big calories and little calories and kilowatt hours. And this is just kind of interesting because it shows some different activities and how much energy those would use. So let's see, like the amount of energy used by a human body running 1 mile. So that would be 4.2 times 10 to the 5th joules, or 1 times 10 to the 5th calories, the regular, or 100 nutritional calories. But in kilowatt hours, it would be 0.12. So just different units of energy.